Hi guys. Now we talk about the Unit 3 chapter classification of elements and periodicity in properties. In that we'll go to cover periodic trends in properties of elements. The periodic trends in properties of elements, many observable patterns in the physical and chemical properties of elements in a descending in a group or move across the period in the periodic table. So there is one trend. For example, within a period, the chemical reactivity tends to be high in group 1 metals. Within a period, chemical reactivity tends to be high in a group 1 metals and lower in the elements towards the middle of the table. Lower in the elements towards the middle of the table and increases to a maximum in the group 17. That is non-metals. So another one more trend is within a group of representative metals like alkali metals, reactivity increases on moving down the group. Second trend, within a group of representative metals like alkali metals, reactivity increases on moving down the group. And the third one trend, within a group of non-metals like halogens, reactivity decreases down the group. Within a group of non-metals like halogens, reactivity decreases down the group. The properties of elements follow these trends based on the theories of atomic structure and properties of the atom. What is about trends? Trends in physical properties. There are numerous physical properties of elements such as melting point, boiling point, heats of fusion, and vaporization of energy, atomization, etc. These shows the periodic variations in the periodic table. The periodic trends with respect to atomic radii, ionic radius, ionization enthalpy, electron gain, enthalpy, and electronegativity. The periodic trends we can study on the atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. So let me discuss about atomic radius firstly. Measuring the size of an atom is very complicated. If you think we take a ball and measure the diameter of that one, so when you're turning the ball maybe slip, but that may be easy, whereas atom measurement is very difficult because atom having a very small size, that is nothing but 1.2 angstrom in size, or even you can call in meter 1.2 into 10 raised to minus 10 meter in radius. Since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. There is no practical way by which the size of an individual atom can be measured. We have no practical way by which the size of an individual atoms can be measured. However, an estimation of the atomic size can be made by knowing the distance between the atoms in the combined state. So, atomic size can be made by knowing the distance between the atoms in the combined state. There is one practical approach to estimate the size of the atom of a non-metallic elements is to measure the distance between the two atoms when they are bound together by a single bond in a covalent molecule. And from this value, the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule Cl2 is 198 picometer, and its half of this distance is 99 picometer. This can be taken as the atomic radius of chlorine. For metals, the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. In non-metallic elements, you can refer it as covalent radius, whereas in metals, you can refer it as metallic radius. For example, the distance between the two adjacent copper atoms in solid copper is 256 picometer. Hence, the metallic radius of the copper is assigned a value of 128 picometer. Atomic radii can be measured by X-ray or other spectroscopic methods. But here we are studying about atomic radius can be measured by the covalent radius and metallic radius. The atomic radii of the few elements, we can list it as like this. So atomic radii per picometer across the period, how it will be there. In the period 2, an atom lithium having a atomic radius is 152 picometer, beryllium having a 111 picometer, boron having a 88 picometer, carbon having a 77 picometer, and nitrogen size having a 74 picometer, oxygen is 66 picometer, fluorine is 64 picometer. See, look at this one. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Across the period, the atomic radius is decreasing. Okay. In same way, in atomic radius in period 3, for example, sodium having 186 picometer, magnesium is 160 picometer, aluminum is 143 picometer, silicon is 117 picometer, phosphorus is 110 picometer, sulfur is 104 picometer, and chlorine is 99 picometer. See, in this period 3 also, you can see the atomic radius goes on decreasing across the period. If possible, you people can note down these things. Atomic period 1, atomic period 3. Same way, atomic radii per picometer down the family. For example, atom group 1. Lithium, same example we will take now. Atom group 1, atomic radius of lithium is 152, sodium is 186, potassium is 231 picometer, rubidium is 244 picometer, and cesium is 262 picometer. See, down the family, the atomic radius is increasing. Lithium is 152 and the cesium is 262. So this is the difference across the period and down the period, down the family, how it is atomic radius is increasing. Same in group 17, fluorine atomic size radius is 64, chlorine is 99, bromium is 114, iodine is 133 picometer, and aluminum is actinium is 140 picometer. There are two trends are obvious. We can see in these two set of examples. To explain these trends in terms of the nuclear charge and energy level, the atomic size generally decreases across a period for the elements of the second period, because within the period the outer electrons in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in that the increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number. The atomic radius regularly increases with the atomic number within a family or in the vertical column of the periodic table. For example, for alkali metals and halogens, as we descend the groups, the principal quantum number increases and the valence electrons are further from the nucleus. This is happen because the inner energy levels are filled with electrons which serve to shield the outer electrons with electrons which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. The atomic radii of a noble gases are not considered here. Why? Because being a non-monoatomic, their non-bonded radii values are very large. Radii of the noble gases should be compared with the van der Waals radii of other elements, not with the covalent radii. Okay. So there is one question. There are some 4 elements we are giving here: magnesium, magnesium 2 plus, aluminium, aluminium 3 plus. In these, which one having the largest and smallest size? So in magnesium, magnesium 2 plus, aluminium, aluminium 3 plus, atomic radii decreases in a period. Cations are smaller than the parent atoms. Among the isoelectronic species, the one with the larger positive nuclear charge will have smaller radius. Hence, the largest size is magnesium and smallest size is aluminium 3 plus. From this atomic radius, we have two more questions. How do you mean atomic radius vary in a period and in a group, and explain their variations? What is atomic radii, or what is atomic radius? This is about the atomic radius, which is one of the variation in periodic trends with respect to the periods. I hope these you people are understood, and please, if not subscribed, please subscribe the channel. If the video is liked, please like the button. Thank you for watching.